We've seen that assuming a particular solution, u1, y1 plus u2, y2, and putting a condition on the first derivative of that particular solution, we can get this equation that we see here, and observing that the three terms circled in green simplify to this, which is just going to be 0 because y1 is a solution of the original equation. And same thing with these three terms. We end up with this plus this equals g of t, this equation. The condition that we put on the particular solution, on the first derivative particular solution, was that this sum be 0. So now we have two simultaneous equations in u1 prime and u2 prime. We're going to solve for u1 prime and u2 prime. We're going to do that with matrices. Now, not everybody in the course knows matrix operations, so I've assigned everybody to solve this without using the matrix operations. You'll get the same thing, just two simultaneous equations. For example, solve this one for y1, and then, well, you go from there. Okay. I'm sorry, we're not solving for y1. Solve this one for u1 prime. That wasn't going to work because you had a y1 prime. Solve this for u1 prime, obviously. Plug that in for u1 prime here so you can solve for y2 prime, for u2 prime. Remembering that y1 and y2 are known solutions, so that y1 prime and y2 prime will also be known. So the only unknowns are the u1 prime and the u2 prime. Okay, you can do that. Now, to do that using matrices, we just rewrite this system as a matrix equation. Now, I've reversed the order of these two so that the functions y1 and y2 occur in the first equation, and y1 prime and y2 prime will then occur in the second equation, and you can easily verify then that this matrix product is totally equivalent to this system of equations. Well, now this is this matrix, this y1, y2, y1 prime, y2 prime matrix, which ought to remind you of the Wronskian, can be easily inverted because a 2 by 2 matrix is easily inverted just by switching the two elements in the main diagonal and then taking this element in the upper right-hand corner and making it negative. So that the inverse of this matrix is just this, but of course then you've got to divide by the determinant of the matrix. Well, the determinant of a matrix, as I kind of alluded to, is the Wronskian. Okay, so dividing by the determinant is equivalent to multiplying by the reciprocal of the Wronskian. The Wronskian, of course, is the determinant of this matrix, which is just y1, y2 prime plus y2, y1 prime. So I'll write it this way, but later on I'll write it as the Wronskian again, but they mean the same thing. So here's the inverse matrix. To solve this equation, we just multiply both sides by the inverse matrix. We get the identity matrix here, so we just get the u1 prime, u2 prime, and then multiplying this by the 0 g of t, well, we get the solution. So again, to solve this, we multiply both sides by the inverse matrix, which will give me the u1 prime, u2 prime equals the inverse matrix times the 0 g of t column vector. The inverse matrix is this, as alluded to here. And then that's going to give us, well, y2 negative y2 prime times 0 g of t gives us negative y2 prime g of t. The row y1 prime times the column 0 g of t gives us y1 prime g of t. We still have the reciprocal of the Wronskian out here. And then we just multiply through by the reciprocal of the Wronskian, and now I'm just going to write that as the Wronskian in the denominator, a little more compact notation. So we have this, and that's equal to the u1 prime, u2 prime, so u1 prime equals this, So then we write that U1 prime equals this, and U2 prime equals this. Now, from that, we determined that, well, if U1 prime equals something, then U1 is an antiderivative of that thing, so U1 is any antiderivative of this expression, in other words, an integral of this expression. And there's no loss of generality if you just leave off the integration constant. Matter of fact, it would complicate things. It has no use, no meaning. So we have this, and then for U2, we have this. Now, the homework, among other things, is to solve the current equation. Okay, that was on a previous video. But the g of t was the tangent of t. Your y1 was e to the 5t. Your y2 was e to the t. And you've got the rest of the equation. So you plug this in and solve it. I'm also going to ask you to solve for the cosine of fancy omega t as your g of t function, because you can easily do that integral. You can wrestle with this integral if you, well, I'm asking you to wrestle with this integral, see if you can do the integration. There is, of course, no guarantee that this expression here is going to be something you can integrate. I mean, it's, derivative is, the integral is going to be defined for most functions, but it doesn't mean you can actually perform the integration in closed form. So that's another mystery. But there's a wide variety of functions that we can perform the integration on, and we'll see a little later on how that gives us some profound results for driven harmonic motion with damping for RLC circuits and for a lot of other things. Okay?